Power supply for TPA3255. The performance of the TPA3255 amplifiers is primarily influenced by four key components. Preamplifier circuits. A well-designed preamp stage is critical. The NE5532 operational amplifier is a standard choice widely used in audio applications for its low noise, high output drive, and minimum distortions. Its excellent DC and AC characteristics make it ideal for high-fidelity systems. The TPA3255 chipset. The head of the amplifier, the TPA3255 chip, must be genuine and pass factory testing. Additionally, the PCB layout should be closely followed the reference designs to ensure optimum performance. Output filter inductor. The quality and size of output inductors are critical. Many budget designs compromises here by using undersized inductors to cut costs, which can negatively impact performance. Power supply. Today's topic. A high-quality power supply is essential to achieve the rated output power. In fact, the cost of good power supply often matches or exceeds that of the amplifier itself. Choosing the right power supply is a key decision for any audio system builder. In this video, I will cover the basic theory every music system builder should understand when selecting power supply. I will also provide hands-on insights into several popular models to help you make an informed choice. So, we will start with the theory. And the first one, RMS value of AC or alternate current. The root mean square RMS value of any AC current is equal to the heating effect of the AC current, and is equal to the heating effect of the DC current. The RMS value of AC is equal to the direct current, which when passes through the resistor for a given period of time will produce the same heating effect as produced by alternating current when passed through the same resistor for the same time. The root mean square value, RMS, of perfect sinusoidal AC voltage or current has a certain relationship with its peak or maximum value. The RMS value of the AC waveform is equal to V peak divided by square root from 2 or V maximum divided by square root from 2, where Vp and Vm are the peak of the maximum values. So here is a mathematical derivation. If you want, you can go through, but I think from engineering point of view, you can forget about it and just use the final formula. So here's the peak value, what we can easily measure with oscilloscope and with other measurement equipment. And here is this RMS value, and we should multiply the peak value by approximately 0.707 multiplier. This also is important table to understand. Waveforms can be different, and music signal is different from sine wave. So that for sine wave we can calculate RMS based on this formula, or we can use a crest factor. What's in reality is just an inverse to RMS. Sometimes we use a crest factor for easy calculations. And you can see for different signals, those are different. And one more important, for a square wave, symmetrical square wave, the RMS is 1. It's the highest one. And you can imagine when we start clipping sine wave, it's becoming more and more similar to square. That means you will get by far more heat from sine wave when it's at the clipping level. And this is why when we are running amplifiers at the clipping level, those are overheating. Either it kicks protection or they will burn. So we need sufficient power that we never hit the clipping. And here I want to draw your attention to a difference between sine wave and real audio signal. This difference between average and maximum peak levels of the mix can also be expressed as a crest factor measured in decibels. So if we go back, here's a crest factor. And we can express in the decibels or the direct values. though the reduction of the peak levels can decrease the crest factor of the mix. So if we compressing music, then this RMS is going up. You can see for sine wave it's 3 decibels. RMS is 3 decibels. We know that those 3 decibels in the values are 0.707. And for audio it is more. It is 12 to 20 decibels. 12 it's 4 times, and 20 is 10 times. So typically we are calculating crest factor of 8 for a music signal. And you can see some guys are taking sine wave, putting that board to measure on a sine wave, and then thermal protection kicks, and they are saying those are bad boards because they can't provide rated power. It's not true, because we are dealing with the audio waveform, and then this heat is much lower. We still have high peaks. Yeah, we should provide full power, but the thermal conditions are completely different. It's important to understand. We can't measure those China boards or any manufacturer in Class D boards at a maximum sine wave, because those are not built for that. Those are built for audio, and thermally they can sustain sine waves. They can perfectly operate with audio signal, and really are capable to do all those peaks in perfect way, but they can't remove heat if you use a sine wave at the peak level. And here is the better picture of the normal audio signal. You can see that the drum kicks are very large, and average RMS power is low. One more thing to understand, and I want to ask a question. What is wrong with those pictures? I will make a pause and try to understand what is wrong with those pictures. Yeah, those are marketing pictures showing how your amplifier will cool, or how air will flow. But you know, when you're heating something, it's never go down. It always goes up. Yeah, you know that some air balloon, when you heat air in that balloon, takes up 3-5 people in a basket without problems. So air is not flowing in this way, and this is a crazy picture. Today marketing, they can lie. Yeah, this is a total lie, totally wrong picture. And here as well, heat is not distributing in this way. All heat from the bottom, where you have that chip, will go up, and all this enclosure will be hot as a hell. And air will not go out of those small holes. There is not sufficient chimney, or not sufficient height. This particular design cooling only by spreading heat through the enclosure. There is no airflow. And how to make an airflow? You just need to turn it in vertical position. Yeah, when you turn it in vertical position, then yes, between those holes there will be nice chimney, and we will start to cool our system. If your amplifier is overheating, just make a stand and put them vertically, and then everything will be fine. Here holes are even better. If you take this amplifier, put it vertically, you can get a maximum power out, and this amplifier will have a nice life. One more thing to understand about from the theory. So when we have a pulse signal, and I said at the clipping we have a pulse signal, and here is a spectrum of the pulse signal, or Fourier transformations of the pulse signal. It's a spectrum. And imagine you are clipping at 300s here, and then you have a second harmonic, and third, and fifths, and many harmonics. And more you're clipping, then more harmonics has it. And those harmonics are at low level, but recalculating, if you have clipping at 300 watts, then each of this harmonic is about 4 watts. Yeah, and those are summing up. And you can see those 4, and there are more, those are in tweeter section. That means if you have a lower power amplifier and you are clipping it at some power, then significant power will be produced in a tweeter. And tweeter efficiency is only 1%, rest is heat, and all those 4 watts plus 4 watts plus 4 watts plus 4 watts, 16 watts will rise significant heat, and 16 watts is significant heat, and your tweeter will be dead in certain time if you really run at a clipping level your system. This is one of the reasons why more powerful amplifiers are never burning your speakers. Here is theoretical model how it happens. Yeah, you're clipping here. Yeah, from sine wave you becoming kind of square wave. You generate all those harmonics going in a tweeter region, and tweeter is dead. And here is just one screenshot from one manufacturer where they measure square wave harmonics just to show that theory and practice they matching. And Tektronix is a good measurement device manufacturing really advanced devices, and it's measured. Yeah, this is measured at 1 megahertz, but the same spectrum is the same. And for audio, we have the same principle. One more thing, when we are looking at the specs, all manufacturers showing you specs at 10% total harmonic distortions, and at maximum 50 volt power supply we can get about 315 watts in stereo. And if you go back, yeah, we can get 300 watts, and we start to generate those harmonics. So this is not exactly area where we want to be, but there is one scenario when we can use it in multi-amplification system or in active systems when each driver is driven by separate amplifier. We can use that power, and that power we need for a woofer. First we have active crossover or filtering frequencies before amplifier, and then we run amplifier at clipping frequencies, and it generates tons of additional components. But for a woofer and subwoofer, our sensitivity to harmonics are low. At 10% total harmonic distortions, we feel nice, perfect bass. And that means this is only scenario when we can use that power range, what this particular chip can do. In other cases, we should be far below. It's about 80% from the maximum power, and then we can get a 260 about. But in reality, we want to be even at a lower power. So once we want to have a good 100-watt amplifier, probably we should aim for a higher power and then use it up to 100 watts. A lot of good words. Also, those low total harmonic distortions at low volume and at 4 ohms. About output noise, it's a good but not excellent. Excellent would be 30 microvolts. Here we have 85 microvolts, but still for most cases those are very good, and generally all parameters are so good. Yeah, those are far better than integrated amplifiers, expensive integrated amplifiers for 80s and 90s. Yeah. And one important thing, our amplifier has 90% efficiency. In calculations we should use, that means 10% will go for heat. Yeah. We are not able to get a full power or 100% power out. 90% efficiency. Let's remember this number. And as I said about the amplifier, about not real power we get. This is graph for 50 volts power supply, and for a 10% total harmonic distortions we get this 300 watts. But in reality, as a high fidelity amplifier, we want to work only in that region. So that means 70% from that maximum power is a maximum where we want to be. And when we are choosing our power supply, we can take voltage, what satisfies that 300 watts, but the power we can take lower. So it's okay when power protection triggers here, because we don't want that additional 10% region. We can damage our speakers. So in that case, 70% from the theoretical maximum power is fine for us. Yeah. So in majority, you know that power we need only for woofer, and for tweeter and mid-range we are working somewhere here. That's very, very good total harmonic distortions. And in that case, multi-channel or active speaker system with a number of amplifiers is giving you very good audio reproduction, because we are working at excellent region here, and for a woofer it's fine to go to the maximum. And here is one important thing why I said that 300 watts are theoretical or very difficult to get it. Here is processor, Intel processor, and I put almost comparable sizes about TPA3255 chip and this Intel processor. And this processor can dissipate 95 watts with a aggressive active cooling at high with a high RPM fan blowing directly to the heatsink, and you can see how big is the surface, and the maximum what this chip can dissipate is 95 watts. Almost limits. If you go higher, then you have bulky solutions and you have water cooling, and then theoretical limit is 120 watts. But it's already very difficult to do that. So standard, no more than 100 watts. Comparing that large surface and that small surface what we have on a chip, you can imagine it's somewhere here, and by surface it's, I know how many, 20 times smaller than that. And this is a major reason why those rated 300 watts, brave 300 watts in many marketing booklets, those are not realistic, absolutely not realistic. Here's a light calculation. Let's assume that we have 50 volt power supply, and we are running 300 watts per channel, and knowing 90% efficiency, that means 10% per channel will go to the heat, 30 watts per channel, and we have 2 channels. We should dissipate 60 watts. And here is answer for those who put sine wave at a maximum for both channels on a load and complain that this audio amplifier is overheating. It should dissipate 60 watts. Come on. Impossible, impossible at any way, and we don't need it for audio amplifier. One more thing, idle heat dissipation. Chip is not 100% efficient, and we have losses. And typically, when you just switch it on and there is almost no music, we still have 2.5 watts at the chip level, and about 2.5 watts at inductor level, and minimum 5 watts. In reality, all board has even more watts to dissipate. I measured the board with the 2 chips and 4 channels, and total idle losses at 48 volts were 17 watts, and the board went pretty hot. We need a good heatsink for that when we aiming 300 watts per channel. Very difficult. And that means when I said we need a really good heatsink, aluminium thermal conductivity is lower than copper, and then there are nice solutions when copper is mixed with aluminium to keep a price right. I haven't seen such type of solutions in a budget board, but really aiming 300 watts, you need them. or you need active cooling with a fan. As I said, we don't need a maximum, we need to work at a 70% from the maximum. Another thing, this is for your personal reading, you should know Ohm's law, and you should know them very well. So read the theory. I will not spend time there. You can stop and read it or find it in internet. But everyone who is dealing or choosing audio equipment should know the Ohm laws principles. And I will draw your attention of the power formulas. So the typical power formula, what we will often use when we know the RMS voltage, voltage square divided by the load, and we can get amplifier power. So, and then you have all the relationships, and you can do different type of calculations. But this is an important formula for you to remember. Here I did basic calculations for our power supply choices, and we will look at the two popular scenarios at 32 volt power supply, what I saw, and 48 volt power supply for 4 ohms and for 8 ohms. And let's look at this table. Here we have a power supply voltage, and typically 32 volt power supplies are 5 amps rated. So the first calculations, we calculate it to RMS value, then we have a load, and then we divide according to Ohm's law that RMS with a load, and we get a current for one channel, and then here is a current at 0.7 or at 70% amplifier load. It's about 4 amps, and then we can calculate a maximum power or clipping power needed. So there are voltage and voltage in square. This is C5, yeah, C5 by C5 and divided by D5. So voltage square divided by load, and we get a power. And since we are not able to get a 100% result, so in reality amplifier is getting only 90%, so we reduce it by that factor. And power at 70% is about 80 watts. So that means we need, if we want to run our system at clipping level, we need a power supply at 230 watts, and at 70% about 150 or a little bit more. Typically those power supplies are able to withstand some additional peak power to the normal power. So if we have 32 volt power supply and 5 amps rated, that we can run only one channel. But normally they are able to do some 7 amps peak, and then we are almost there. Theoretically we need 8 amps for this 70% current, but we have capacitors which are helping to power supply to give those additional amps for a base, and then power supply is working. So this particular power supply, 32 volts and 5 amps, practically are able to provide you for 80 watt output at 4 ohms with a normal confidence. And that's a good parameter. But you understand that for 8 ohm load, when you have 32 volts power supply, you get only 40 watts. Yeah. 32 volts, 5 amps power supply, you can get a good 40 watts. And how about popular 48 volt solution? There are great power supplies, even up to 10 amps. And you can see if we really want a 4 ohm load and full power, we need 10 amps rated, 48 volts power supply. And we can get out really excellent power up to 180, up to 200. And on 8 ohm load we can get nice clean 90 watts. And then we need 48 volts 10 amps, and for For 8 ohm load we need 48 volts, 5 amps. Yeah, and then those power supplies, they are capable of some extra peaks and good large capacity electrolytic storage capacitors on a board. Those help to get confident calculated loads. So this is a maximum. Don't believe those 300 watts what you have in promotions. So theoretical maximum for TPA3255 is 200 watts per channel. Great, excellent, 200 watts per channel on 4 ohm load and 100 watts on a 8 ohm load. That's the limit. For multi-channel system, yes, you can go to clipping, but then you need by far a more powerful power supply. I would say peak power should be for your power system at least 15 amps capable. Yeah, 15 amps capable. Then you can get really this full power out to drive some subwoofer. And here is a typical power supplies what you can get. It's 48 volts, 5 amps, popular, and those power supplies are good supplied. Those are specially designed, and this theory what I told comply. Yeah, and practically everywhere you have 48 volts, 5 amp default power supplies. And mostly because that design is not able to dissipate more power. Yeah, there's no reason to give 48 volt 10 amps power supply, because then the system overheats really to drive it at such a power. No reason to do that. You remember, here is a picture why it is not possible. There is no airflow. You need a fan. Yeah, then you need a fan, and then you can go with a higher power. Actually, with the same board. You can put more aggressive cooling system, and then you can have this high power out of it. Yeah. The same 48 volts, but 10 amp power supply, and you need additional cooling. The best audio amplifier power supply architecture is LLC, resonant converter. You can read in internet. I will not spend time here. Because they have one specific, the current what is flowing through this power transformer is pure sine wave. There is resonant contour, but you can educate yourself about that. And second thing, the all stabilization is coming just changing frequency, not pulse width, and this is not low noise principle, how to stabilize voltage. And where is the difference? This is a classical flyback where we're working with a pulse width, and it generates tons of or emits tons of noise, and you should suppress it, and then you have heavy filters at the output. Bulky system, and it's hard to stabilize because music is non-regular. You have short-term high peaks, and then you need a lot of energy, and then you have this moderate average vocals and high frequencies when you need a few watts, and this is such type of architecture is not good for audio power supply. And here is one choice what I made for built-in boards. This is meanwhile a low profile 300 watt series power supply. It meets all necessary criteria for audio power supply. Almost perfect. This is industrial. It's produced in huge volumes, and meanwhile is a Taiwanese nice manufacturer with the factories in China and Malaysia and everywhere. And let's take a closer look to this series. Here is technical documentation, and we will look here. So this model produced in large volumes has several standard voltages output, and I'm interested personally only on those two. This LOP336 fits very well for a 4 ohm load, no fan operation. yeah, because then everything is balanced, and it can provide at a peak for 3 seconds 12 amps. It perfectly fits. You remember this table, you can go back and look at it. This peak amp capability is really important, and this power supply can do that. So we are using 300 watt power supply, but at peaks it can do 450, and it really can. And there is no thermal problems with that. It's running almost cold due to this audio signal crest factor of 8, because this is built to really drive LED system, yeah, continuous consumption, and it can do, yeah, peaks 450. With a fan it can do 300 watts, and without fan 180 watts, and we calculated our maximum consumption is about 45 watts. It's running cold, and all parameters are perfect, and low noise, and everything is so good. It is medically certified. It has all European American certificates that you can build a system and sell it to those countries. And this is industrial board. Great choice to build in some systems when you are making these TPA3255 amplifiers. There are some pictures. Also, this is low dimensional board, and really state of the art to make such power in so small size is something incredible. And they are using double-sided relatively expensive technology, because here you do some surface mount, and then you should do this coordinate soldering system. It's not a cheap or not a budget board. It's really great board. And then we have several offerings in a market, and this is branded as AIMA DC4810 amps capable power supply. Pretty bulky, but this is a good one. It is developed by and manufactured by other company. This is just branded like that. Practically for all China, this TPA3255 type amplifiers, they are using the same power supplies. Those power supplies are good. They have PFC, they have low noise, and they are capable to deal with the amplifier type of signals. Those are good. But you see, it's pretty big. Often it's bigger than the amplifier itself. And I see it seems even has a fan inside. There's another one, Fosse Audio, famous small amplifier manufacturer from China. And they are using this 48 volt and 5 amp power supply. It's popular. Not very cheap, I would say. Pretty costly. And then I found that in my point of view, pretty good amplifier, 36 volts, 6 amps. Then you can get 100 watts out of your system. Very good. I have it, I tested. I will show you it in practice as well. And now let's take a hands-on on some of those power supplies. No, this is my favorite. And I will start. This is 450 watt capable audio power supply. Because those peaks are important, and this is built in a way how we need. Because if you take 450 watt standard power supply, it will be very big. And this one, look, 105 millimeters. Jeez. Yeah. 50 millimeters. So easy to integrate. So good. This is really state-of-the-art engineering system, and you can see maybe, yeah, here. It has all those specific architectural windings of this power transformer LLC power supplies. It has LLC power supply and it has PFC. And how it is working, that PFC is multiplying input signal from 110 or 220 to 400 volts, and then this power part is working from PFC stabilized at 400 volts. An additional advantage is that when you have a PFC, you are storing energy in capacitor and you are also storing energy in inductor. For me, it's hard to recognize where is it. Maybe this one or something beneath here. Not hard to say. Anyway, you are storing energy in two places. And that means when you need this instant peak, it is so easy to transfer. You even don't need additional large capacitors. You can drive boards with a small capacitors on board. There are some boards where you are saving on the capacitors. Very good. Also for your safety, there are two melting surge protection. You can use it for a medical. If something happens with this power supply, then those blow up and there is no voltage on chassis, so you will not get any problems with that. And low leakage, it is allowed to use in a medical equipment in this as well. Fantastic board. I was so happy when I found it. And the last thing, it produced from the good manufacturer, really famous in the world, and it produced in large volumes. And even new model will come. There will be the same dimension, the same type of power supplies that you can replace one-to-one in the future. So this continuity, it is important as well. So if you build something and something happens with that, you can easily buy a new one, and you can easily get a replacements when end of life will happens. Everything here is excellent. Yeah, you can feel I'm really happy about this design. And here we have this AIMA power supply, and you can see it is 36 volts, 6 amps, and it is excellent power supply of this 36 volts because it can do this 70% of maximum power with a confidence. It can do clipping power. It can't. It switches off. But maybe it's not a bad thing. Maybe it's a good thing. Yeah, it's saving. It's protecting your tweeter. But you can see that maximum power what we can make is about 216 watts. And some extra peaks, but not much. It's really switching off if you give a clipping power. But anyway, this is a really good power supply. I didn't find anything to complain. It also has a PFC in it, and it is working reliable, not overheating. Also compact design. And I think it's done by some good manufacturer. It's definitely not this amplifier company who designed it. It's designed by some champ. Yeah, it's designed by some champ. And I recommend it. Those are good power supplies. If you want more, then there are versions with 48 volts, but those cost more. Where to buy? Those are popular power supplies, and you can buy them on Amazon, you can buy them on eBay, you can buy them on AliExpress. I took Amazon as a popular internet shop system, and here I put some internet search keywords, and I give this AIMA DC 48 volt 10 amps audio power supply. It's okay price. Yeah, you can't find them very cheap, and as I said, that power supply often costs the same as amplifier, and in some cases even more. And also when you are buying this 10 amp 48 volt power supply, you should be confident that you will be able to cool your system. Also, you should honestly answer to yourself, do you need such a power, or it's okay with 48 volts and 5 amps or 36 volts and 6 amps. If you have 4 ohm load, then 36 volts 6 amps is better choice than 48 volts and 5 amps. And what else? Here I put the same keywords, but with a Fosse and Fosse audio. You can see here is a 48 volts 5 amps power adapter. A bit pricey, yes. And Fosse, somehow Fosse brand is more expensive, but those are the same. I think the same company is producing, and the same architecture and the same designs are in those power supplies. All of them are okay. You can buy any. And do we have that Minwell LOP300 48 volt power supply open frame? It's also on Amazon. I found one. It's about a 50. Here it is, and you have some description about everything. You can buy such a board and put in a box, and also it will be great for you. At least for this board, I know that it has this LLC architecture, and it's really small comparing to those power supplies. It's very small in dimensions. Okay, and now, having all theoretical background, let's look at the one example and find out what is marketing saying and what this amplifier really is capable. And here is a good amplifier for very good price, in my opinion. And what they are saying: AIMA A07 premium, blah 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 blah, 300 by 2 amplifier with DC 32 volt power adapter. And here marketing really has no limits. The output power up to 600 watts, and we know that practically it's not possible. You can't cool a system, and we know that this package is coming with DC 32 volt 5 amp power adapter, which is really balanced for that design, and it's right power supply. You don't need to upgrade it for more powerful. If you want to upgrade for more powerful, you can do it, but then you should consider cooling upgrade, and I think there is no way except direct fan which is blowing on the chassis. If you choose that system, then you should accept that for 8 ohm load you have 40 watts power, and for 4 ohm load you have 80 watts power, and then your system is balanced. And 80 watts clean power is very good power. You can drive even relatively large floor standard and listen from 2 to 3 meters, and it's more than enough for near-field monitors. So overall it is balanced system, and it's coming with the right power supply. So I hope this knowledge was valuable for you, and when you want to something upgrade, then you know why you are doing and what you are gaining after that.